Hi everyone. I'm very happy to be here with you, and I'm going to be talking to you a little bit about supermassive black holes, which is the subject of my PhD. But first, I want to introduce myself a little bit. So I'm Stephanie Buttigieg. I'm Maltese, but I am a student at the University of Cambridge, and I study supermassive black hole mergers. And hopefully, by the end of this lecture, you will all understand all those words, what they mean, and what it is exactly that I study, and why it's so exciting. I'm also a big advocate for women in science. I love sharing my kind of my journey in academia as a young woman on my Instagram account. So if you wanna go check that out, then I'd be happy for that. And you might be wondering how I ended up giving you the lecture. And you might recognize this person who I know that she would be annoyed at me showing this picture. But that is Agnesa. And me and Agnesa met at CERN when we were both doing an internship around 2 years ago. So even before I knew what supermassive black holes were. And this was when we were building a cosmic ray detector at CERN. So if any of you have the opportunity to do that into the future, I would highly recommend, because you make really great friends and you learn really cool physics. So on the topic of cool physics, let's start with something that's a little bit closer to Earth. I'm not going to mention black holes yet. I want to talk about escape velocity. So I can't really, if I was in the room, I'd ask for a show of hands. I can see you very small, so maybe we can do this. Can I have a show of hands of who knows or has heard of the concept of escape velocity? Okay, so quite a lot of you, I think, from what I can see. You're really tiny on my screen, so I might be wrong. But the concept is pretty clear, right? So if you throw a ball into the air, that ball will fall back down. Why? Because the Earth is a massive object, it has mass, and it has a gravitational force or a gravitational field, and it pulls everything down. But it's not impossible to escape the gravitational field of the Earth. And we're lucky that it's not, because we like to send things out into space to study space. But we have this concept of an escape velocity. So there's a minimum velocity at which an object needs to be moving for it to escape the gravitational field of Earth and go out and travel to wherever it wants into space. And I'm not going to derive where this equation comes from, but we have a very nice, simple equation that can give us the escape velocity of an object, of a planet, for example, or of a star. And this equation can be given by the square root of 2 times the gravitational constant. So this gravitational constant is just a number, which I will give you the exact value for in the next slide, and it is constant everywhere in the universe, so this one doesn't change. And then m, which is the mass, in this case, that's the mass of the Earth, and the radius r, which is the radius of the object. In this case, it's the radius of the Earth. Now, it turns out that if you put the numbers in, and I'll give you a time to do this in the next slide as well, we find that the escape velocity of the Earth is 11.2 kilometers per second. So that's per second. And so that's quite a large velocity, but it is a velocity that spacecraft can reach. And this is how they escape the gravitational field of Earth. Now, I want to move away from Earth, and I want to take you to the sun. Obviously, metaphorically, not quite literally, because that wouldn't be a great idea. But I want you now to calculate the escape velocity of the sun. So here I've given you your equation for the escape velocity. I've given you the value of the gravitational constant, and I'm telling you that the mass of the sun is 2 times 10 to the 30 kilograms, and the radius of the sun is 6.96 times 10 to the 8 meters. So I'll give you some time to work this out, and when you're ready, put your hands up, and the people in the room will help me, and they will tell me your answers. So have fun calculating. Do we have any answers?
Als 620,000
Correct, yes, exactly. So the point here I want to make is that when you compare that to the Earth, right, which has an escape velocity of 11.2 kilometers per second, the Sun is a much more massive object, and it has a stronger gravitational force, and so you need even more velocity to escape the pull of the Sun. Now I have one more calculation for you, and then it will just be me speaking. Now I want to change it up a little bit, and I want you to calculate rather the radius that the Sun needs to have. So imagine that the Sun doesn't have the radius that it does, and it can change. But what is the radius that the Sun needs to have to not allow light to escape? So if that means that if light cannot escape, then the escape velocity needs to be at least as large as the velocity of light, which I'm giving you here. It's 3 times 10 to the 8 meters per second. So I'll give you some more time again, and I want a value for the radius that the Sun needs to have. Yep, do we have an answer?
Yeah. 2,964.
The going answer is 2,964 meters, right?
Yeah.
Meters, yes, that is correct. So when you divide that and you change it into kilometers, we get 3 kilometers, right? So the point here is that if we condense the mass of the Sun, which is really, really heavy, right, 2 times 10 to the 30 kilograms, if we condense it in a small enough region, the force of gravity of the Sun becomes so large that light wouldn't be able to escape. And if light cannot escape, then we wouldn't be able to see anything, right? And this is the exact concept behind a black hole. So a black hole is an incredibly dense region in space. So think about condensing a mass that is way, way larger than the mass of the Sun, condensing it in an area that is so, so small that the escape velocity becomes larger than that of light, and nothing can escape. So that's the definition of a black hole. Now, a black hole is formally defined through Einstein's theory of general relativity, and we will see a little bit better later on in the lecture what that means and what the consequences of those are. But there is two important parts of a black hole. So the central region, which is called the singularity. Now, the singularity, no one knows what it really is. Physicists are trying to come up with theories to explain what is going on, but we just don't understand it. And the reason why it's so hard to understand what the singularity is because it is hidden by the event horizon. So the event horizon is a radius around the singularity where if you fall into the event horizon, there is no way you're going to escape the black hole. And even more than that, if you fall beyond the event horizon, your future becomes the singularity. So whatever happens, you will end up going towards the singularity. But we cannot see anything because light cannot escape. The escape velocity is way too large for light to escape, and so we have this black hole. Now, black holes, we've kind of known about them for a while, and they come in two main flavors. So we have stellar mass black holes, and these are the kind of light ones. So these have a mass of around 10 times or maybe 30 times even the mass of our sun. And I will explain where these come from. We understand them pretty well. But then there's another flavor, and these are supermassive black holes. And these are the cool ones, in my opinion. And the reason why they're so cool and why they're so puzzling is because they have a mass which is around 1,000,000 to 1,000,000,000 times the mass of the sun. So now you might understand why I've titled my lecture Cosmic Giants, because they're really giant objects. But I have to be a bit careful actually with my choice of words, because when I say they're massive, that means they're really, really heavy. But it does not necessarily mean that they are also very large, because black holes are very condensed. So they actually occupy quite a small region in volume and space, but they contain this really heavy mass. And how do we even know about them? Because I just told you that light cannot escape, so we wouldn't be able to see them, right, with our telescopes. And that's kind of true, but I'm going to show you a video, and yes, it's playing, and I hope it's playing well. This is showing the orbits of stars around the center of our very own Milky Way, our very own galaxy. So astronomers just grabbed their telescopes would just observe normal light, and they pointed them towards the center of our galaxy. Let me play that again. And what they've seen is that there are stars that are kind of on really strange orbits. So I don't think you can see my pointer, but if you focus on the stars that are in the central region, some of them are going really quickly around something that we cannot see. And this is a speed up of the orbits, but there is a star that has an orbit of only 20 years around the center of the galaxy. And astronomers kind of work backwards, because we understand gravity quite well. So we can model what kind of mass is causing these stars to orbit in this way. So with that specific velocity and with that specific periodic time. And we can infer that there is an object in the center, which we cannot see using normal light, but that has a mass of around 1,000,000 times, over 1,000,000 times the mass of our sun, and is condensed in a very small region of space. And that's exactly what I told you a black hole is. So this was the very first evidence that there is the presence of a supermassive black hole in the center of our galaxy. And this discovery, which was made in the 90s, so a while ago now, but very recently in 2020 won the Nobel Prize for Physics. And there was Andrea Ghez and Reinhard Genzel that shared this Nobel Prize. And as a fun fact, Andrea Ghez is the 4th woman ever to win the Nobel Prize in Physics. And I'm a bit curious, so there's a total of 5 women that have won the Nobel Prize in Physics. And I'm really curious to see if anyone can mention at least one other woman that has won the Nobel Prize. Marie Curie, yes. Marie Curie won it, and she was the woman that won both the Nobel Prize in Physics and Chemistry. But yeah, there's another 3 women, apart from Andrea Ghez and Marie Curie, that won the Nobel Prize in Physics, so I urge you to go and look them up and learn something interesting. Okay, so back to supermassive black holes. So you might have seen this image sometimes. Let me do a show of hands again. Has anyone seen this image before? Okay, quite a few people again. So this is the very first image that we took of a black hole. But what they didn't say is that this is a supermassive black hole. And so this is not a stellar mass black hole that we took an image of. And now, once again, I can imagine what you're thinking. I just told you that nothing can escape a black hole. A black hole literally has a name, a black hole. So we shouldn't be able to see anything, and we didn't see anything in that video that I showed you, right? But when a black hole, in the region surrounding the black hole, there's such a strong gravitational force and also magnetic forces that when material that is kind of falling into the black hole, it starts kind of orbiting the black hole, and there's a very large temperature, a very extreme environment around the black hole. And so the gas and the dust and any stars that kind of get ripped apart, they start glowing because they get really hot. And this is the same concept as friction, right? If you rub your hand together, they start warming up because there's friction. And in these extreme environments, these particles also start radiating energy. And this is what we're seeing around the black hole. So we're seeing this kind of accretion disk, or rather the glow from the material that's falling into the black hole. And the reason why we can see this one and not in the other observations is because we're observing at different wavelengths. So light has different wavelengths or frequencies. And if we look at longer wavelengths, which is what the Event Horizon Telescope does, so if we look at the radio frequencies rather than the optical, then we can see this glow surrounding a black hole. Now, this specific black hole, so the very first one, is the black hole that's in the center of the galaxy called M87. But we also have, which I think is cooler, is a picture of our very own black hole, our very own supermassive black hole in our galaxy. And this is called Sagittarius A star. So this is what we're seeing in this image over here. So I think that's really cool. And the Event Horizon Telescope is still kind of out there. They're still observing using radio telescopes on Earth to find even more black holes and to kind of try and build a video of a black hole to kind of really study what is going on around the black hole, because we still don't fully understand it. Okay, so we went from these black holes being invisible essentially to potentially, if we look close enough and with the right things, we can maybe see them. And that's true for some of them, which are quite dormant. They're quite kind of just laying there, not really doing anything. But black holes, supermassive black holes, can be some of the brightest objects of the universe. Or rather, I should say, the supermassive black holes can be fueling the brightest objects in our universe. And these are called active galactic nuclei. So what does this mean? So galactic just means galaxies, right? Nuclei means nucleus, the plural of nucleus, so the center of the galaxy. And active means that something is going on. There's some source of energy that is making them really bright and energetic. And this source of energy is the supermassive black hole in the center. So here's an image of Centaurus A, another galaxy, and you might have noticed those kind of jets that are kind of exiting the plane of the galaxy. And those are coming from the supermassive black hole in the center. So because of the strong gravitational and magnetic forces surrounding the black hole, the light can really be accelerated and can be collimated, we say, so kind of shot out in these jets. And these outshine such a small region in the galaxy, but it can be outshining the whole galaxy itself. And these are really interesting objects, and thanks to these, we can study the population of supermassive black holes even very far away, because if an object is really, really bright, you can still see it from very far away. So these allow us to gain some insights on the population of supermassive black holes that is in our universe. But something that is really, really cool is that, well, you can imagine, right? I've just shown you that image where there seems to be a lot of energy that's being kind of pushed out into the galaxy and into the surroundings. So somehow, if the black hole is kind of talking to the galaxy, and maybe the galaxy is talking to the black hole itself. And this is what we see. So we've observed quite a lot of galaxies in our local universe, and when I say our local universe, I mean the galaxies in our neighborhood, in the neighborhood of the Milky Way. And we've kind of started seeing a trend. So here I've got a graph, a schematic graph, but it's very informative. So on the y-axis, you've got the mass of the black hole. So all the way from no black hole at the bottom, and then you grow your black hole. So for example, 1 million solar masses, so 1 million the mass of our sun, or even 1 billion solar masses. And then on the x-axis, so horizontally, you can see the mass of the central bulge. What does this mean? So in a galaxy, we have different components. And one of the components is that there is a stellar bulge. And as you can see kind of in the image, there's kind of like a group of stars surrounding the central regions of the black hole. And this can be kind of separated from the rest of the galaxy. And what we see is that the more massive the black hole in the center is, the more massive the bulge surrounding the central region is. So there must be some communication between the black hole and the galaxy in a way. And it's not just the mass of the central bulge; it can also be the brightness of the central region of the galaxy. So there's a very tight relationship between the two things. And this is great when you look in the local universe, so in the region that surrounds the galaxy, our galaxy. But now we have new observations. Some of you might recognize this telescope. So it's the James Webb Space Telescope. This was launched quite recently, I think in 2021. And what this telescope is really good at doing is it's really good at observing galaxies that are very, very far away. Now here I need to explain an incredibly important concept in astronomy. And that is that when we look far away, we are also looking back in time. So the reason for this is that light has a finite velocity, right? I gave you the value of the velocity of light. And even though this is really, really fast, it's not infinite. This means that I can see that you're probably looking at the screen, right? So the light from the screen is reaching your eyes. And because light travels so quickly, that distance between you and the screen is traversed really, really quickly. So you don't notice any delay. And this is kind of in general on Earth, the distances aren't large enough for us to notice that light travels at a specific speed. But if you look at the sun, for example, we are seeing the sun as it was 8 minutes ago. And this is because space has incredibly large distances that our minds cannot even comprehend. But here, the finite velocity of light becomes important. And light takes time to travel. So the nearest star to the sun, if I'm not mistaken, is 4 light years away. So that means that light takes 4 years to travel from that star to us. And we can keep going like this. If we keep going further away in distance, we keep going further and further back in time. And the James Webb Space Telescope is brilliant at seeing these very early galaxies. So we look at galaxies, some of the earliest galaxies that we've observed with the James Webb Space Telescope are around 13.8 billion light years away. And for context, our universe is around 14 billion years old. So that means we're seeing the very first galaxies that have started forming in the universe. And we can also look at the black holes that they have, because we want to understand whether those galaxies also respect the same relation as the galaxies and the black holes that are very near to us. And actually, we have a bit of a problem. Well, not a problem, actually something that's quite cool, but something that's quite different in the past. That in the past, the black holes seem to be bigger in relation to their host galaxies. So they wouldn't lie on this nice diagonal line, but they would lie above it, where I've put the image of the telescope. And this is kind of very confusing, because does that mean that the relationship between the black holes and the galaxies can be changing in the past? Probably, maybe. We've started seeing, so there was a recent discovery actually from my department at the University of Cambridge, that we found a black hole that has a mass that is larger than all of the stellar mass in the galaxy. So think about it. If you add all of the stars in the galaxy, they are still not as massive as the central black hole. So that is just crazy, because we don't see that in our local universe. And this kind of starts pointing towards the question of, where did these black holes come from? Maybe have they always been this big, or did they grow just really quickly at the start of the universe? And to answer this question, we need to take a few steps back, and we need to go back to stars and stellar evolution, and understand where normal black holes form. By normal black holes, I mean stellar black holes, so those small siblings of the supermassive black holes. So this is kind of a nice summary of how stars go through their life, from the way they are born all the way to the point where they die. So they are born from a nebula. A nebula is just a cloud of gas that somehow cools down enough for it to start collapsing under its own gravity. And then when it starts collapsing, then it can form a star. And a star can form with various different masses. Including low to medium mass stars, which includes our sun, or high mass stars. So if we focus on the top branch first, so the low and medium mass stars, the stars when they are burning hydrogen into helium and then helium into heavier elements, we say that they are on the main sequence. So they are behaving just as we expect stars to behave. But the fuel that's in stars doesn't last forever. And when it starts running out of fuel, it evolves. And towards the later stages of its life, it can form a red giant. So this is when it kind of, the star really grows in volume. And for example, for the sun, it will grow so much that it will engulf even Earth. But we don't have to worry about this. The sun it's quite young, so we're okay. But once it burns even more of its fuel, nothing can support it, because when it's burning hydrogen into helium, for example, it's creating what we call radiation pressure. So this radiation pressure pushes the star outwards. And this balances out the gravitational force that is pulling the star inwards. But when it runs out of fuel, there's no radiation pressure, and the star just collapses in on itself. And because of that kind of shock, it creates what we call a planetary nebula. It doesn't have anything to do with planets. I'm not quite sure why they call it a planetary nebula, but these are really beautiful objects. If you look planetary nebulae up on Google, you'll find some really nice pictures. And then once it kind of sheds out its layers and all the elements and heavy elements that it created during its lifetime, you end up with a white dwarf. A white dwarf, you can think of it as kind of this dead star that doesn't really do anything. So that's not super interesting for our case. But what's really interesting if we go for the high mass stars. The high mass stars have a similar lifetime. They kind of life cycle, and they burn hydrogen into helium and helium into heavier objects up until it reaches iron. And then once it reaches iron, it doesn't really make any more sense for them to keep burning. And so they kind of collapse under their own gravitational force. And because it's more massive and the shock is larger, then they create what we call a supernova. So supernovas are really bright objects in the universe as well. And in this phase, this is where they shed and they spread all of the heavy elements that they've created. So like carbon and iron and even heavier elements are created during this shock. So for example, gold. And they kind of spread it in the region of space around them. And then this material creates more planets and stars and moons. And this might be why we say we are made up of star stuff. Because every single element that's in your body was created in a star. That's the only place that we can create these heavy elements. But that's kind of a tangent. If we now focus on what happens after a supernova, depending on the mass of the star that was originally started this process, you can either end up with a neutron star. So these are really, really dense objects still, but they're not quite black holes. So their escape velocities are not quite large enough for it to be as equal as light. And these neutron stars I will mention them again later, so do remember them. Or if you have a very high mass star, you can form a black hole. So astronomers are pretty happy with this explanation. We know that this is how stellar mass black holes form. So those smaller kind of black holes. But these can have about maybe 10, 30, maybe 50, if we're lucky, times the mass of our sun. But how are we growing supermassive black holes from these really light black holes? We need to grow them really quickly, because we know that the James Webb Space Telescope is seeing the really big black holes. So somehow we need to grow them really quickly. And this is a question that researchers are still trying to understand. We actually don't know where these supermassive black holes are forming from. But we have some theories. We're working on it. And one of the theories is that we have light seeds. So the word seed refers to what the black hole started as. So just kind of like an analogy with like a seed of a plant. And the light seed theory thinks about forming these black holes in a very similar way to as what I just explained in this previous slide. So what if with the first population of stars in our universe is called population tree stars, which is kind of strange. It's kind of not very intuitive, right? Because they're the first population of stars, but we call them population tree. So don't try and understand what astronomers name things after. But these population tree stars would have been quite different from the stars that we have in our universe today, because there was only hydrogen and helium for them to form. They were the ones who created those heavy elements, and then the stars that we have nowadays would have already had some heavy elements. So they look quite different. But population tree stars, we think, can actually form quite massive in the first place. So they can be up to 1,000 times the mass of our sun. So way more than what a present-day star would be. So okay, so maybe you have this really massive star that would then collapse and form a black hole, but you still have a black hole that is 1,000 times the mass of our sun. We need to grow that to 1,000,000 times the mass of our sun. So in that way, we would need what we call high accretion rates. So black holes eat things. That's how they grow. They, whenever something falls within its event horizon, then it has no escape and it gets eaten by the black hole, and then the black hole takes on that mass and it grows in mass. So this is what we call accretion. But there is physics that we know about that limits the amount of accretion, so the amount of growth that can happen at a specific time. So we cannot have these black holes growing super quickly. But if we were to grow them from very light seeds, from these population tree stars that collapsed, we would need those high accretion rates. So is there something in the physics that we don't understand that would allow us to grow them really quickly? Maybe. But another explanation could be that we have heavy seeds. So these are seeds that would start off already quite large, so already closer to that million solar masses. And there are some ideas about how these heavy seeds could form, and this would take us away from the fact that we know that all black holes in our universe formed from a star. So maybe that's just not true. Maybe there could be a giant gas cloud, for example, that somehow avoids fragmenting into individual stars. So that's what we think should happen. We think that the kind of gas should form different stars. But maybe somehow there's a process that is bypassing that and is allowing that gas cloud to just directly collapse into a black hole. Or maybe we have some runaway stellar mergers. So stars bump into each other. This is common in our universe. And if you're in a region where there is a high density of stars, maybe from this gas cloud that has already collapsed into individual stars, maybe those stars can just start kind of merging with each other at a really high rate and create a heavy seed for a supermassive black hole. But we just still don't know. So this is a very active field of research. And actually, very recently, we had this new result come out. And this is called the Infinity Galaxy. I think probably because it kind of looks like an infinity symbol. And what we see over here is two galaxies that are merging with each other. So we'll talk about more in detail in that in the next slide. But galaxies can merge with each other. And what they think is that when the gas from the shock front, so where the galaxies are making that impact, could be collapsing into a direct collapse black hole. So we could really be seeing the birth of a supermassive black hole in this. But we're not sure, right? We still don't know. This is something that is very far away, and we need to make a lot of inferences from the light that we get from the telescopes to actually understand what is going on. So maybe we're seeing the birth of a supermassive black hole, but maybe something else that we don't understand. And as I said, I will talk a little bit more in detail about galaxy mergers. So galaxies, I've kind of mentioned them quite a lot, but galaxies are a collection of stars and gas, and I think you had a lecture about dark matter, is that correct? Just before this. So it's a collection of dark matter, gas, and stars. And we live in a galaxy, right? Our Milky Way galaxy. But galaxies merge with each other all the time. Our own galaxy is on track to merge with the Andromeda galaxy. That's kind of on the way to us. But I told you that galaxies have supermassive black holes in the center. And actually, we kind of think that every single galaxy has one. So this is just for illustration purposes, by the way. They're not as large as that. But if we have two supermassive black holes in the centers of galaxies, and those galaxies are merging, then they're taking their supermassive black holes in with them, and the black holes could form what we call a binary system. So two black holes that are orbiting each other. And these could eventually also lead to mergers. So two black holes, two really heavy black holes that merge with each other and give off gravitational waves, which I will talk about as well. But this is exactly what my PhD is in. So I try to understand what happens when two galaxies that have two supermassive black holes in the center come together, and how can we bring those two black holes towards each other. And that is exactly the question that I asked in my PhD. How do we shrink the binary separation? Because think about it. If the Earth is going around the sun, right? That's a binary system. Let's forget all the other planets that are also orbiting. Imagine we just have the Earth and the sun. That's a binary. And the Earth is pretty stable. So the orbit of the Earth is quite stable. So we're staying at the same distance away from the sun, which is very good news for us, because I wouldn't want to be falling in closer towards the sun. But if there is a process that takes away energy from that system, so imagine something that is slowing down the Earth loses velocity and it would fall towards the gravitational force of the sun. So this is what we need in supermassive black holes. We need processes that take away energy from the binary of the two black holes so that the two black holes can shrink towards each other and potentially even merge with each other. And these, there are various different steps into how we shrink this orbit of the binary. And I will go through them one by one. And these kind of span as well very, very large distances and very, very small distances. So there's a lot of different physics that is going on here. But the very first stage, as I've kind of showed you in the previous slide, is when the host galaxies themselves, this is what we call the galaxies that are hosting the black holes, are the ones that are coming towards each other. And I'll explain what dynamic friction is in a second. But this is the kind of very first stage that brings the two black holes together. But the two galaxies, at some point, they merge and become one galaxy. And the two black holes are kind of swimming in this remnant galaxy that has merged from the two mergers of the two individual galaxies. And here we need dynamic friction. Now, what does dynamic friction mean? Imagine you have a really heavy object, like the black hole, that is traveling through a background of stars. Let's just imagine stars for now. What happens is that this black hole is going to pull the stars, and it's going to pull the stars behind it, in its wake, we call it. So I've kind of illustrated that as kind of a bit of a flame. So imagine that flame, that's kind of how the stars are being pulled towards the black hole. But then those stars also have gravity. And so this kind of starts a tug of war between the black hole and the stars. So the stars are pulling at the black hole and they're slowing it down, and the galaxy and the black hole keeps going and it keeps collecting more stars and it keeps slowing down. So this is how the two black holes are losing energy and they're slowing down within the galaxy. Great. At some point, this becomes inefficient. This process can no longer keep going, and we need another process. So at this point, the two black holes are close enough together to feel each other's gravitational force. And now they are moving together through the galaxy as one pair. So they're no longer just individual black holes, but they are this system of orbiting black holes around each other. And then we need other processes that take away the energy. And the first process that kicks in is stellar scattering. This is really fun because when a star comes in, if it has a low enough velocity, the star interacts with the binary black hole and it gets given energy and it gets kicked out. It literally gets booted out of the system and it gets given energy, right? Because it gains velocity, and that doesn't just come for free. Energy is conserved in the universe. So the star gets given energy and the binary loses energy and it shrinks slowly. But the amount of stars that can interact with the binary in this way is quite limited. So at some point, we will run out of stars that can help us shrink the orbit of the two black holes. And then we need gas. So around the central regions of the galaxies, there is usually quite a lot of gas. This is not always the case, but when it is, this can help us shrink the orbit even further. And this is quite simple to understand. Imagine if you're swimming, right, in the sea. When you go in a liquid, you feel that kind of drag force, that slows you down. This happens even if you go skydiving, for example. The air, the atmosphere of the Earth is a fluid, and it slows you down if you're kind of falling. And this is exactly what happens. So those two black holes that have what we call a circumbinary disk, because it kind of envelopes the whole binary, they're kind of swimming through this gas, and they're losing energy as they're doing so. And finally, we get into the regime where they're close enough together to give off gravitational waves. Now, what are gravitational waves, and why do they matter? So at this point, then, that is when they merge and they create a black hole that has a mass that's equal to the mass of the first one plus the mass of the second one. So an even bigger black hole. But what are these gravitational waves? So far, I've mentioned the electromagnetic spectrum. So you've probably seen this in school. But light has different wavelengths, different frequencies, and that can give you different flavors of light waves. So you have the gamma rays, which are the most energetic kind of light rays that there are, and then you've got the radio waves, which have really long wavelengths. And recall that that is what I told you, that we observed those images of the black holes in radio frequency range. And then we've got the visible light, and here, like, I've just picked an infographic that kind of highlights where the different telescopes also observe. Because when you see images from a telescope, they look nice, and you kind of assume that that is exactly what the things look like in the universe. But that might not be true, because, for example, the James Webb Space Telescope does not actually observe in the visible wavelength. We observe in the infrared. So that's kind of the light that comes from your remote control to control your television. And then we give colors to make sense of that, because our brains can only understand visible light. But the point here is that electromagnetism is a spectrum, right? So we've got the spectrum of waves, and this is how we historically looked at the universe and understood it. Astronomers always went and looked through telescopes, and then they kind of made inferences about what they're seeing. But now we have a new probe of the universe, and rather than seeing the universe, we have now started hearing the universe. And you might be being like, what is she talking about? So I told you that when we made that calculation with the escape velocity, it was quite a simplistic approximation. But if you want to really understand where the black hole as a theoretical concept comes from, then you need to understand Einstein's theory of general relativity. And in this theory, Einstein imagines the space as kind of this fabric of space-time. And then when you put something heavy in the center, so imagine if you stretch a sheet, and then you put something heavy in the center, that sheet kind of dips down, right? And that's the force of gravity. And people realize that in this theoretical framework, if you have two heavy objects that are orbiting each other, you can create these ripples, which I'm going to play again. So you can kind of create these waves that are emitting from the system of orbiting black holes, that is kind of really distorting the space-time fabric around the two black holes. And then they give off that big burst of gravitational waves. And gravitational waves carry energy, so that is why the very last phase is driven by gravitational waves, because they keep carrying the energy away from the binary up until they merge with each other, and then they give off that big burst of gravitational waves, and then it settles down. But what these gravitational waves do is that they distort the space-time, right? So they're changing the distances that we measure. So when gravitational waves pass through the Earth is kind of going like this, and then like that, like this, and then like that. And then this effect is incredibly small, so it affects nothing. But we can detect it, and we have detected it very recently. And you might be being like, so this is around 1,000 of the radius of, or the diameter of a proton. So a proton is already a teeny tiny object, and now 1,000 of that, that's the kind of sensitivity that we need to have to detect gravitational waves from two black holes that are merging with each other. And how do we do this? So we do this using lasers and light. So we've built gravitational wave detectors that have quite long arms that are forming an L shape. So kind of what I'm showing over here. And these gravitational wave detectors, they shoot a laser from one end of the arm, of one arm, all the way to the end, and then it gets reflected by a mirror, and it gets shot back. And in this way, we can measure distances. And how can we measure distances? Based on constructive or destructive interference, which you might have come across. So we can think of light as a wave, right? It has a crest and a trough. Now, if we have two light waves that are overlapping with each other, which, for example, we have when we're shooting a laser from one end and then reflecting it back from the other end, then the light waves can align with each other in different ways. So if we have them aligning exactly perfectly together, then we have what we call constructive interference. And what happens here is that you have light that is even brighter. But if the two light waves interfere with each other in a way that is the opposite, so the peak in one of them is the bottom in the other, then they cancel out and we actually don't get any light whatsoever. So this is exactly what the team at the LIGO-Virgo collaboration, that's the very first gravitational wave detector that was built, they do. So they shoot light, and based on whether the light is getting more bright or just disappearing, they can measure the distance. And if they measure a distance that is different from one arm than another, so if one arm is being squeezed, but the other one is being stretched, then that might be a gravitational wave that they're detecting. And we need to make sure that this is actually a gravitational wave and not, for example, some lorry that is driving above the detectors. And because of this, we have two different detectors, and they're separate from each other, so they're on opposite sides of the United States. And if both of them detect the same thing, then we're like, something might be going on. And then we go to Einstein's theory of general relativity, and we can model what these vibrations should look like. And if they match, we've detected a gravitational wave. And actually, we have. And I'm not sure if I'm sharing my sound with you through my through the presentation, but can you hear that?
No.
No. Then 1 second. If I
Yes.
Okay. Can you hear that? Yeah, so that is the sound of two black holes merging with each other. And that's really cool. So now we're not just looking at the universe, but we can hear the universe. And just like when I go back to this one, I've made it very clear that this is a spectrum, right? There's different frequencies and different wavelengths. In the same way, gravitational waves, if I skip through all of these, also have a spectrum of frequencies. They give off different frequencies, and this is the same as sound. Sound has different frequencies, right? That is why if I go lower with my voice, that is a lower frequency, and if I go higher, that's a higher frequency. And not the problem, but the kind of issue with black holes is that if you have more massive black holes, then they give off gravitational waves which are lower frequency. So we move towards the right in this plot. So you can see in the bottom there's emerging stellar mass black holes in other galaxies, and those are detected by the ground-based experiments. So those are the experiments that are in an L shape that I just explained how they worked. But this is the problem. So we've detected those stellar mass black holes merging with each other. But we haven't yet detected supermassive black holes merging with each other because the frequencies that they give off are outside of the sensitivity range of that telescope. Just like, for example, the James Webb Space Telescope here wouldn't be able to see the radio waves because it's just not built for that. And in order to be able to detect lower frequencies or larger wavelengths, we need longer arms. So we need even longer distances where we're shooting those lasers between each other to be able to see that change in the distance that the gravitational waves are causing. But the Earth is limited, right? The Earth is the Earth. We can't just make more space on Earth. So we need to go up into space. And this is exactly what the European Space Agency is planning on doing, and now formally planning on doing, and started planning this mission. And this is called LISA, which is my favorite ever telescope, even though it doesn't exist yet, and it's technically a gravitational wave telescope. But LISA stands for the Laser Interferometer Space Antenna. It's not important. But what's important is that, I have a better slide for this, is that LISA will be 3 spacecraft. So we will launch 3 spacecraft, and we will put them in a triangle, orbiting around the sun, so after the Earth. So imagine just the Earth and then this LISA constellation passes by. And in between these spacecraft, we will be shooting lasers, and we can measure the distance. And by measuring the distance, we can measure how the gravitational waves are distorting space. So how they're kind of distorting the triangle, the triangle as we see in those kind of top images. So they're elongating one arm and vice versa. And this will have the perfect frequency range to detect gravitational waves from supermassive black hole mergers. Can I just ask, how much time do I have left?
18 minutes.
Cannot hear anyone.
18 minutes.
Oh, okay, that's great. Okay, so so this is one of the ways that we can be able to detect gravitational waves from 2 black holes merging. And why is this so important? Because we cannot really see black holes at very small separations with our normal telescope. So with the telescopes that use light. Why? Because when objects are very far away, if they're very close, you wouldn't be able to resolve it. So it would just look like one big blob to you. But we want to be able to see the 2 black holes separately. And we wouldn't be able to do that with light. So this is why we need gravitational waves, which from the signals that we receive, we can, for example, say how far away they are from us, say the masses of the 2 black holes and of the black hole that comes out at the end. So we can really understand a lot of things. And we can also start understanding where those supermassive black holes are coming from. Because gravitational waves, they don't get blocked by anything. They can just pass through the entire universe at the speed of light still, but we can be able to detect them. So if something's happening far away, so far back in time, we will be able to see it with LISA. And if we go even further down the frequency, so even longer wavelengths, we actually have something really, really cool that we can use. So at this point, we cannot really keep building spacecraft that are further away from each other and shooting lasers in between them. But we can be smart. And we can use objects called pulsars. And pulsars, remember I mentioned those neutron stars that could be one of the things that come out when a star dies if it's not big enough to form a black hole. So pulsars are just specific type of neutron stars. And they give off this electromagnetic radiation in these beams, and they rotate. And they rotate really, really accurately. So some of them rotate really quickly. So for example, millisecond pulsars, where the rate of rotating is literally milliseconds. Some of them can be a bit longer. But what's really cool about them is that they're very accurate. So we can use them as cosmic clocks. And this discovery was actually made by one of my favorite physicists or astronomers, Professor Dame Jocelyn Bell Burnell. And Jocelyn Bell Burnell was a PhD student in Cambridge as well. So this is why I really like her. And she worked with radio telescopes. So we actually have some radio telescopes that are a bit further away from Cambridge, and I've actually gone and seen them. And she made observations, and she was looking at her data at one point, and she saw these blips. And they were like really, really regular blips. And actually, if you see her notes, you can see she wrote LGM, which means little green men, ? So as a joke, she was like, oh, are these aliens? They aren't. They're just pulsars that rotate really quickly and are really good at keeping time. So what astronomers have done now is that we've built a pulsar timing array. What does this mean? We found loads of pulsars that are in our galaxy. They're just there. They're just sitting, waiting for us to use them as accurate clocks. And we're looking at them very regularly. And we're looking at the rate at which they rotate. And if we measure slightly difference in what we call the time of arrival, so if they rotate a bit slower or a bit faster, that might be because there's a gravitational wave that is passing through that pulsar and the Earth and is changing the distance between us. If you change the distance, then you're going to mess up the time it takes for the light to travel, right? Now, this process is quite messy, so we can't really do it with just one pulsar. But if we observe multiple different pulsars, and we see a pattern or a correlation, we call it, between how the light is being delayed or sped up, then we can detect a gravitational wave background. And this gravitational wave background is essentially loads of supermassive black holes that are merging together, and all of their gravitational waves that are being emitted, they're kind of overlapping with each other, and they're creating a hum. So rather than that really quick noise that I told you that I've made you hear, so that brrr, so that's just one event. But if there's loads of events at low frequencies, it will create something like and that is exactly what we're trying to detect using this pulsar timing arrays. And what we've actually kind of managed to do, so we have very strong evidence that there is a background that is kind of being sourced by these supermassive black holes, but we're still not quite 100% sure. Well, we're never 100% sure in astronomy, but we need to be like 99.999 something percent sure. And we're still working on getting more data because this is a very slow observation. You just need to keep looking at the pulsars and seeing what they do along very long periods of time to confirm that there is an actual gravitational wave background. But the gravitational wave background depends, the properties of it depend on the properties of the black holes that are merging. So how many are there merging? How quick is the process that they merge? What are the actual processes that bring them together? What are their masses? How far away they are? And that is what I do. So I try to model what background, gravitational wave background, these supermassive black holes will create. And this is the very last slide, and then I'll open up the floor for questions. But I do this using what we call cosmological simulations. And these I find are really cool things because you're essentially having a universe in a computer and all the data from that universe is just available for you to use and manipulate and play around with. So cosmological simulations are these really large simulations that model how stars and gas and dark matter and supermassive black holes interact with each other and how they form galaxies. So this is a real image that I produced myself from the data, and this is kind of showing you a very, very big picture, the galaxies in this model universe. So it's not our universe, it mimics our universe. And the bright regions is the galaxies. So all those dots that you're seeing are galaxies. And on top of these galaxies, I'm marking them just with white stars, but these are all the black holes that I have in my simulation. And my simulation is able to track where those black holes are going and how they are growing via accretion, which I mentioned, and how they are bumping into each other and merging with each other. But then you need to really be careful with the data because this is very coarse. So as you expect, we cannot model every single process in the universe because otherwise it wouldn't be a simulation, it would just be our universe. So you need to make some assumptions in the simulation. So then you take the output of the simulation and you investigate it. And you add, for example, all those different, if I go back, I add all the effects of, where are they? Not here. All these effects. So I model all of these effects, for example, and see what added time delay they're adding. And then out of that, I can make predictions for number one, Lisa, and number two, for pulsar timing arrays. So now I hope you understand what I mean by when I say I study supermassive black hole mergers and what supermassive black holes are and why they're so cool and how we'll be able to learn about them in the next kind of 10 to 15 years as the European Space Agency launches LISA and as we get more data using pulsar timing arrays. So thank you very much for your attention, and I think I have quite a lot of time for questions.